If you find it difficult to keep up with the fast pace of the AI race, or you're consuming a lot of superficial AI content,
then you're at the right place. Here we discuss the state-of-the-art AI which you can directly integrate in your industrial applications and also in your daily life. Welcome to Networks and Graphs. Today we'll be talking about machine learning.
Exactly. And from a little bit more general standpoint. So what we are going to talk about is what is machine learning and what happened. Everything has been influenced by AI.
Yeah, ChatGPT, man, that has taken over everything. Like starting from small businesses to social media, like everyone's using ChatGPT, like even in writing their content and probably taking exams, right?
Exactly. And then, here is the real surprise, at least to me, because AI has been around for a while and it's been doing great works in different domains and industries. So what is it that is really special about the transformers architecture?
It's transformers. Transformers have been around for a while, but for ChatGPT, I think the huge training data set, first of all, and also human in the loop. Tuning your model to be more humanistic, to get answers more similar to humans. That's a game changer right there.
That's a great point. Human in the loop versus the transformers architecture. But before going to the nitty-gritty, let's step back a bit and ask ourselves, can we even categorize machine learning algorithms in a diachronic sense or in any other sense? What is the most accepted categories of AI ML algorithms?
Yeah, there are a lot of ways you can categorize machine learning models, but the most common one that is well accepted across the community is supervised learning and unsupervised learning.
Right, so supervised and unsupervised. What it really drills down is, do we have labeled data or unlabeled data? What do we mean by label?
Labeling means you have some category associated with your data points, right? For example, if you are designing machine learning models on say medical images, like say MRI scans, right? Like whether some patient had a disease or didn't have a disease, like that is like 1 and 0. So these are labels which you can use to identify different categories of your data.
Exactly. In a recent work that I have done in my postdoc in Northeastern University at Network Science Institute, we actually had some labeled data on food processing. There has been researchers that categorized food into 4 different categories, 4 different labels. Unprocessed food like apple, and then culinary ingredients like oils, and then processed food like canned food, and then ultra processed food like, for example, a ready-to-eat macaroni and cheese.
And that's a great example. And how this example is different from the one I gave, like I had only 2 labels, right? But Babak's work had 4 labels. So it's a multi-class classification problem.
Exactly.
Right.
And the issue here was, so giving credit to the people who created these labels, the Nova researchers from Brazil, it was a very important contribution to the society, to the food systems. And what is really important here is the imbalance. The number of ultra processed food, the proportions of them, is extremely imbalanced. There's like 70% of the foods in grocery stores are ultra processed.
Yeah, so you're saying that for supervised machine learning, when you have different labels, right, removing different biases in the data, for example, the class imbalance he was talking about, that's a big part of data processing and data engineering, which is absolutely important for making unbiased supervised predictors.
Exactly, because if there is bias in your data, then that bias will be reflected in your machine learning algorithm as well. But when machine learning engineers, scientists, when they see labeled data, like when we saw labeled data, labeled foods in 4 categories, the first thing we do is we search for features. We search for different aspects of food. For example, the concentration of nutrients, and see if those features can predict the label.
Yeah, that's a part of feature engineering you're going into, right? So
Yes.
trying to figure out the labels, the things that you're trying to predict for a certain class of data. What are the independent variables there? What are the features that can predict there, right? For example, what did you say you had, like a concentration of different nutrients?
Yes, that's exactly what we use. We just use 12, depends on the panel, 12, 15, 20 nutrients concentration. We did not use the ingredients at all. It could be incorporated, but the beauty here was that the machine learning was able to actually predict with a high accuracy the labels, the levels of processing as 4 categories only by using nutrients.
That is a great point. So, like, if you wanna kind of map this problem that Babak solved in his research paper to like high school mathematics, so it's like you're trying to find a function which takes as input all this nutrient information, the concentrations and all that, and at the output predicts the labels for like ultra processed food or like unprocessed food and so on, right?
Exactly. So this was an example, a more detailed example of what is a supervised algorithm and what is a labeled data. How about unsupervised, which in our previous video that we are going to link here, we did talk about the t-shirt sizing problem.
Unsupervised learning, like the t-shirt sizing problem that you mentioned, right? So unsupervised learning means you don't have any label, right? So you don't have any reference data to train your model on. So your model has to learn from, I think of it as the geometry of the data. Like clustering is a form of unsupervised machine learning, right? So you identify different clusters of the data points in the space. So you have no reference data, but still you're finding out some important patterns from the data that you have.
Exactly. So there are things that we take for granted.
Yeah, like for example, fraud detection. Like, so if you're, say, receiving a lot of emails, or like you're receiving a lot of like hits like on your server, whatever, then there are algorithms which can identify like whether certain emails or like certain ping requests, like they're different from the others, right? So like you can cluster the good ones and then cluster the bad ones. So this kind of anomaly detection, right? So you don't have the labels for them.
Exactly.
They're also unsupervised in nature.
And as you can just see from just this conversation, now we are going to different types of machine learning algorithms. For example, anomaly detection. That, is it completely unsupervised or supervised or semi-supervised?
Learning in general is a really complex task, and this complexity is well captured in the evolution of the machine learning models, which we'll discuss right now. So what you're seeing on the screen is a tree of different kinds of machine learnings. As we discussed earlier, machine learning can be two types overall: supervised with labeled data and unsupervised with unlabeled data. Now, say unsupervised learning has different kinds of approaches in that. For example, clustering, the t-shirt sizing problem that Babak was discussing. There's another domain of unsupervised learning called representation learning, where you try to learn vector representations, like latent representations of different entities. For example, my research is on protein binding, say, right? And there we try to learn a vectorized representation of the protein structures and the amino acid sequences. So that's a part of representation learning. On the left-hand side now, on the supervised learning part, you have things like classification, like what we discussed, like understanding processing of food items, or understanding whether there is a tumor in an image or not, like things like that, right? And then there's a thing called end-to-end learning, which has been pretty classical, like you pass the whole data through the whole architecture at once and train all the weights all together. So that's kind of an end-to-end learning. But now people are coming up with better methods than end-to-end learning. And there were like classic papers too, which talked about things like pre-training, which I'm going to discuss in a bit. And then again, under supervised learning, you have things like one-shot learning, where you have very little amount of data but want to train a model again. Then you have self-supervised learning, where you again have small data but want to train your model with that small amount of data to gain moderate accuracy. And there are different kinds of machine learning out there which are a combination of both supervised and unsupervised learning, right? For example, pre-training. Pre-training can be of many types. So classically, what pre-training used to be was that you had deep neural architectures like autoencoders, right? And they used to train the different layers one by one. So first train the first layer with all the data, then stabilize the weights there, and then you append another layer and like train it. So this is kind of a supervised fashion, right? Pre-training.
It's like incrementally training.
Yeah, and it was shown that like the weights kind of saturate pretty quickly, like if you pre-train the previous layers. And there is a new concept of pre-training of attributes recently. I've used that in my research too. And that is kind of an unsupervised. So you don't train the model in an end-to-end fashion, but rather do the representation learning through pre-training first in an unsupervised fashion, and then you have a supervised component appended at the end of the pre-training part, right? Then you have semi-supervised learning, where you kind of like try to generate new labels from limited amount of labels, and then you have two-shot learning, the things we are talking about. And there is another thing called reinforcement learning. Now, if you are reading, if you have read certain machine learning books, like some of the books consider reinforcement learning as a separate type of machine learning. But you can also think about reinforcement learning. So what is reinforcement learning? You have an agent which moves through an environment to learn certain patterns, right? And then you can give some award to the agent, like if they're doing it right.
It's like an agent-based exploration of an environment and trying to adopt there and evolve there. And as you can see, even we are trying to find a categorization of machine learning algorithms and say, okay, this, for example, two-shot learning is a type of supervised and unsupervised, and trying to do the same for other types of, but then as you can see, it's already getting so convoluted. Our mind is already blowing.
Yeah, the arrows are going everywhere, man.
Yes, like it's becoming a hairball itself, and it's a very, very complicated task, because again, learning is complex. And to make it even more complex, whatever we talk about was just based on approach.
Yeah.
So how about based on a data type? Then it's going to be natural language processing, because
on language data, right? Text data.
Exactly. All these approaches can be implemented there as well. Computer vision, and our favorite, graph machine learning.
On network data, yeah.
Exactly, which is an emerging field, recent field, and very promising field. What is it really boiling down? It's boiling down into generalizability. What is the relationship between data quality and generalizability? So let's stop hanging on the tree that we were trying to create.
So far, we have talked about different kinds of machine learning approaches, right? But again, Babak mentioned that all these approaches can be on different kinds of data: natural language processing, computer vision on images, and then graph machine learning and all that, right? But the different categories of machine learning is one thing to discuss, but what we feel that a more important thing to discuss about machine learning models is the quality of data and the generalizability, right?
Exactly. That's what exactly it's boiling down to. The quality of data, how can we measure that? How can we assess that? We already give some hints, like what is the degree of imbalance in the data we have, what is the size of data we have, and all that. And generalizability.
Yeah, and generalizability is so AGI, right? Artificial General Intelligence is a dream. And so far, what we have learned about generalizability and transferability. So transfer learning is another domain of machine learning. So what we mean by generalizability is that how well can your model do beyond your training data? Like how good can your model perform on unseen data?
Never seen before, exactly.
For example, like if you're designing self-driving cars and you train the car in the roads in the States, can you drive that car in China, the roads on China?
Exactly. Or
if you have an LLM model, right, which you train on, say, financial data, but can it write a poem?
Yeah. Can it learn from financial data to say a
About
beautiful Bukowski, a very, very meaningful poem?
Yeah, I don't know.
Yeah.
It might happen. Now let's dive into the notion of generalizability without going into much of the mathematics behind it.
Exactly.
And we also try to understand the generalizability notion with respect to the training data, and especially the quality of the training data that we were discussing earlier, right? Well, of course, like the holy grail of machine learning is that you have limited amount of data, maybe not that good quality, but still you can design a machine learning architecture in such a way with great engineering skills that is like highly generalizable.
And this has been started long ago. It started on the domain of statistics, very, very old field. But the focus in statistics was how can we do a lot with limited number of samples.
Yeah.
And as you can see in this diagram,
so understanding the population from a small sample. Estimation theory, right?
Yes, exactly. How can we estimate the population characteristics taking a small samples?
Yeah, I really liked it. Like mapping it back to the classical estimation theory.
Exactly. And then as you can see in this diagram here, the amount of data was very poor back in the day because of not having access to computers, engineering, and etc. But a lot of genius, smart statisticians were able to even generalize into population on that amount of data and derive meaningful information. But the question is, what if you give out of distribution data, never seen before? How would the predictions do?
Yeah, never before seen data, right? Like which you, for example, one of my recent papers, like where we're trying to predict protein-ligand binding. And if you have a new kind of a disease associated with a new kind of a protein which weren't like studied before, or there weren't many drugs developed for that protein before, and if you want to design a new drug, then that is kind of not in the training data. You don't have much training data on that, right?
Exactly.
So how can your machine learning perform well in this kind of scenarios?
So the problem is even more complicated than we think. So we initially thought that having more data would help generalizability.
Not necessarily, right?
Exactly.
Overfitting.
Exactly. As you can see here in this diagram, the amount of data is increased twice more than before. And generalizability is just increased a little bit more.
Yeah.
Many reasons. And one of the reasons is the amount of data doesn't matter, as we discussed before. The quality also matters, and the architecture, which Ian is an expert on.
Yeah, and recently a lot of research. So if you read the recent papers from the top machine learning conference, there's a lot of papers, like there are a lot of papers dealing with this out of distribution prediction. So this is a really important problem, and we need to solve this thing to take us step forward towards AGI, towards artificial general intelligence.
So what is our goal? As you said, AGI is like the holy grail that everyone wants to achieve. That's the next wave. But what is the goal? The goal really is, as you can see in this diagram, to be able to generalize further using limited data. And why using limited data? Because we are always going to have limited data. Observation, always, no matter how much you have better microscope.
And data is expensive, man.
Yes, it's expensive.
And also, if you're collecting more data, doesn't necessarily mean that you're increasing the diversity in that data. So you're getting new kind of data.
Right? Even sometimes by observing a system, you're actually changing its behavior.
Yeah.
So there are little different curses that you need to deal with.
Yeah, and think about humans, right? Moving towards AGI, humans can solve new tasks without being exposed to it like previously. So that creativity, kind of an intelligence,
Exactly.
Yep.
So here, we're trying to find a balance, and we are trying to ask questions like, what data properties and how much data is needed to have a generalizable algorithm.
Yeah.
And what are the upper bounds? Like, how, given a data set, can we tell what is the maximum amount of generalizability you can have? These are the kind of questions that it needs to be solved before we even talk about AGI.
Yeah, people are trying to like answer this kind of questions, like, and integrating like things like information theory and all that into machine learning to have this kind of answers, right?
Exactly.
Yeah. Okay, since now we have established how we should evaluate machine learning models, not in terms of the approach, but rather in terms of the generalizability and the quality of data it is trained on. Let's look at some of the state-of-the-art models which have gained a lot of popularity recently, how they do in terms of the quality of the data and generalizability.
Exactly. Where do they fall in the diagram?
So DeepPurpose is a machine learning model which is used to predict binding between proteins and small molecules ligands. But what we saw in our research was that the generalizability of this model wasn't that good.
Exactly. In fact, what was observed was if you go ahead and give DeepPurpose only the patterns of bindings between proteins and ligands, the small molecules, that's enough. Its performance is going to be exactly the same as if you also give it the protein sequences.
Yeah. So it was learning from the drug-target interaction network rather than the molecular structures.
Yes, some sort of a shortcut to learn from.
Yeah, we call it topological shortcuts.
Exactly. So that means that it does well on proteins that have a lot of interactions with drugs, the proteins that we have a lot of known, basically they are targets to many drugs. It does well for them. And then the proteins that do not have many target drugs, the algorithm doesn't predict well enough.
Yeah, yeah. So as a solution, we developed AI Bind, which learns the binding patterns, the binding mechanism from the molecular structures, and doesn't rely on the topological shortcuts that Babak mentioned. That's the network structure of the drug-target interactions, right? And due to that reason, since you eliminate the topological shortcuts from training, you can predict really well on unseen drugs and unseen proteins in this case.
It's really important to hear that we mentioned the databases used is exactly the same.
BindingDB data, pretty common.
Exactly the same databases has been used. But Ian was able to increase the data quality by finding a smart ways like network-derived negatives.
And unsupervised pre-training, the pre-training we're talking about.
That basically decreases the amount of imbalance in data, forcing the machine learning to not learn shortcuts.
Yeah.
And that's why we placed AI Bind a little bit higher in terms of data quality. So that what really changes is not the number of proteins, it's not the number of drugs. It's really some smart ways to increase the quality of data.
And it's pretty surprising that DeepPurpose, it's like humans, right? So if humans can achieve something by shortcuts, they're going to try to take the shortcuts.
Exactly.
And the machine learning also tried the same, right?
Yes, it's cheaper. If you learn shortcuts, you don't need to spend a lot of energy.
Yeah.
Yes. So looking at the food processing paper that we have done, predicting the degree of processing from food, it's pretty generalizable. The generalizability is high because we trained this algorithm only using the USDA model foods, and then we went ahead and tested on thousands of foods from grocery stores on just the food labels.
So beyond your training data set.
Yes, exactly. And it did well. So then it's generalizable. And the important part here is we are just using a random forest. You don't really need to use a neural network.
Yeah. So the feature engineering you did combined with a random forest classifier and the data pre-processing and the data engineering that you did on the USDA data,
like transformers and all that,
all that combined like improved the generalizability, and you can use that on like any kind of food items probably, right?
Exactly. So really depends on the problem. Do not always search for neural network architectures.
Yeah, if you don't need AI, don't incorporate it. Yeah. If a simple regression does your work, go with a simple regression, man.
Yes.
Continuing the discussion that we just had, all the state-of-the-art AI machine learning models can be placed in this data quality versus generalizability diagram. You can see like ChatGPT has a really high quality training data, but the generalizability is okay, pretty good.
The ChatGPT, I can see a lot of times it's hallucinating. Like
everyone's talking about it.
Yes.
Of ChatGPT. I had some examples too.
Yes, a lot of times I'm asking for references for responses, and it just creates references that do not exist, or even very simple tasks like add two numbers, 2 plus 5. A lot of times it cannot do it.
And sometimes the ChatGPT creates URLs that don't work. I don't know where that comes from.
Yeah, and all this comes back to the fact that there are many ways that things do not work, only a few ways that things do work. And when you interact with large language models, because it's your language and you talk with it, you can spot. You can sometimes or often spot that the response doesn't make sense.
Yeah. And another GPT model, DALL-E, which is used for creating images, creating pictures, right? So I asked DALL-E to create a Led Zeppelin album, and it created this, like where it couldn't even correctly pronounce Led Zeppelin or like have a meaningful album art. So, it completely depends on what kind of training data and what kind of labels you have during this kind of trainings, like whether your model will be generalizable or not. So generalizability and AGI is something we need to more talk about,
As you can see here, like, Ian is a Led Zeppelin fan. I'm not, but I like your work. You can see that the AI can't even write Led Zeppelin right. It even have typo. It even has typo there, and Ian, you can tell better. Is it by any measure of a stretch of imagination related to Led Zeppelin? What you see here?
No, and the art quality is like bad, man.
So what we are really saying here is, when it comes to art, you can tell it's generalizable or not based on the domain knowledge that you have. And then looking at self-driving cars. They are still struggling to have self-driving cars operating in extreme weather conditions, like snow. And that's why we see a lot of self-driving car companies are in California, where the weather is stable. It's perfect for them to train. So then the generalizability is an issue there as well.
Yeah, just imagine taking those cars on an Indian busy road, like where there are a lot of humans and animals walking around. That is the toughest test.
Exactly. But if the road is shared not only by humans and all other beings. We will get back to these topics in the future videos as well. The goal today was to set the baseline of how should we look at AI ML algorithms.
And in order to achieve our dream of AGI.
Exactly.
What we should focus on.
What are the questions to focus on? Like, can we come up with an upper bound for generalizability? Can we quantify data quality? And etc. And in the next videos, we are going to talk about metrics, performance metrics in machine learning algorithms.
Yeah, sometimes they are deceiving.
Exactly. That's why we started to first talk about generalizability before talking about performance metrics.
And never judge a book by its cover, and never judge a machine learning model by the accuracy.
Oh, yes, exactly. We will get into that. Until next time, thanks a lot for watching.
And keep up the network thinking.
Indeed.